Okay. Hello. Happy afternoon. It's afternoon here. It's 3:30. Okay, so this is the second part of the geosphere module. Um, and in this case, so our first video was about plate tectonics. If you haven't watched that one, start there. I think plate tectonics is by far the most foundational topic to discuss in geology, which is why I chose to talk about it. But we're a geology class, so this module or this video is all about the rocks and the rock cycles. And in Geology 101, I actually normally spend about 3 weeks talking about the rock cycle. So this is a very condensed version. And I've picked what I think are the most important parts of this topic to discuss as part of this module. So the topics we're going to cover are earth materials, what that means, minerals, rocks and the rock cycle, igneous rocks, sedimentary rocks, metamorphic rocks, and then we're going to put it all together and sort of look at these proponents as part of Washington State. This is some new vocabulary that you will get to learn today. So let's start with earth material and Henry. She just ate. I don't know. She's been like this all week. I don't know what's going on. She just wants love. Okay, earth materials. So the most basic division of Earth's materials include minerals and rocks, and those are two very different things. Every rock contains evidence of how and where it forms. So this is what I love about geology is that these rocks tell such incredible stories. Um, and give us such a really interesting insight into Earth's history and to the different environments that have come before us. So we use chemical composition and physical characteristics to determine how and where a rock formed and the rock's geologic history. We have to start in talking about rocks by first discussing minerals. We cannot talk about rocks without talking about minerals. So what is a mineral? Um, what I'd like to preface in saying is that rocks are minerals, but minerals are not rocks. Oh, hi. Thank you for that. So a mineral, like quartz, so this is a quartz crystal to the right here, are defined by the following characteristics. They must be homogeneous or made up entirely of the same material or look the same. Homogeneous means the same. They are naturally occurring. So what I will say is this definition has changed throughout history, especially in the scientific community. And naturally occurring was a very broad sort of definition of a mineral. So we've sort of altered this into being, yes, it has to be naturally occurring, but via Earth's geologic processes. Now, mind you, that can still be very broad, but that was a little bit more refined. Inorganic, so not alive, basically, not a living, breathing entity that has a lifespan per se. It has to be a crystalline solid. Um, oops, okay. So when I say crystalline solid, and I go into this a little bit more in Geology 101, a crystalline solid is basically, it's called, we break it down into a very set structure that is called a crystal lattice. And that's sort of what it sounds like. It sort of looks like a ladder. It's a bunch of like molecules that are kind of fit together like Legos almost. And it forms this like blocky crystal lattice structure. That is a crystalline solid. It has a definite chemical composition. Quartz is silica oxide, SiO2. It also has certain physical properties. So if we were to look at different minerals, we would see different hardnesses, we would see different colors, perchance, we would see different strengths of these minerals. And they all have very specific properties where if you're out in the field and you're like, gosh, I don't know what this mineral is, you can test some of these physical properties out in the field. Sometimes it's magnetic, sometimes it reacts to acid. So physical properties are a big identifying characteristic of a mineral. Which brings me to one of my favorite topics, because in geology, uh, there's a really big sort of back and forth between a lot of geologists regarding, well, okay, given this definition, read this definition, is ice a mineral? And it's sort of an inside joke in geology. I don't think there's any actual like, well, maybe there's a lot of ego in science, but at least on my level, I think it's more of an inside joke. Is ice a mineral? You tell me. It follows all of these definitions. So by definition, technically, yeah. But it's ice, right? It melts. It's a solid of a water molecule. So it's just sort of a fun anecdote. These are common minerals. So in Geology 101, you guys would get to play with them and like touch them, and it's really fun. These are very common minerals that we see on Earth's surface very frequently. And a mineral, again, it's a set crystal lattice with a set chemical formula. These are what make up rocks. So quartz is the second most common. I'm spitting this out of my butt, but I know quartz is one or two, is either the first or second most common mineral on Earth's surface. Plagioclase is either tied or it's first or second. It's one of these two. Plagioclase, feldspar, and quartz. These are the two most common minerals on Earth's surface. Um, and all of these minerals will come together in some capacity and form a rock. So again, minerals, these guys, make up rocks. Rocks are like mineral soup. These guys are very specific, and a lot of times we do find these minerals um, sort of in their pure and individual form, right? But in a magma or in a tectonic or geologic setting, a lot of times these minerals get sort of combined together, and the combination of minerals is what makes a rock. And that's what we're going to jump into now. So rocks and the rock cycle. So the definition of rocks are interlocking crystals of minerals, like the granite. So this is a granite. Um, I chose granite because it is probably one of the most common and uh, most identifiable rock. Because we make granite countertops, right? Hopefully you are familiar at least a little bit with granite countertops. So this is a granite. And as you'll know, we have these chunks of different colored minerals within this feature, within this rock. So rocks are formed with interlocking crystals of minerals, when there are fragments of pre-existing rocks, when there's organic material that come together and lithify, which we'll talk about, or other rocks. And there are three types of rocks that we are going to talk about today: igneous, sedimentary, and metamorphic. If you have Disney Plus, uh, you should, and you have the time. I do show my Geology 101 Magic School Bus episode, and it's actually from the second Magic School Bus series they did a few years ago. Magic School Bus Rides Again with Kate McKinnon as Miss Frizzle. It's excellent. And oh gosh, I don't remember the title of the actual episode, but it's early on, and basically it's a time capsule episode, and they're drawing a superhero cartoon to the rock cycle. And it's actually a really good depiction of the rock cycle put into really simple terms. So if you have the chance to watch it, if you need a little bit more sort of in-depth discussion on what the rock cycle contains, watch it. It's great. I make my college students watch it and they love it. Who doesn't love Magic School Bus? So here's the rock cycle. And it is exactly what it sounds like. It is a cycle. There's no beginning, there's no end. The Earth is, as we learned in the last video, is constantly moving, is constantly changing, is constantly recycling itself. And so because of this, we have rocks forming all the time. We have rocks changing all the time. And we have rocks being destroyed and then recreated. So we're going to go through this whole rock cycle in this PowerPoint. But this is one of my favorite depictions of it because I think it's really simple and well put together. Oops. And what I really love about the rock cycle is I have broken it down even further to the stories that these different rocks like to tell. Igneous rocks, which are the first rocks that we're going to talk about, they tell the story of Earth's mantle. So they usually come from very deep within the layers of the Earth. Maybe not all the way down into the mantle, but at least upper mantle, the asthenosphere, as we learned in the last PowerPoint. Igneous rocks, they tell a story of inside the Earth, which is so cool. Sedimentary rocks, my favorite rocks, They tell the story of Earth's surface up here on the very, very top of the continental crust of the lithosphere. And then metamorphic rocks give us a really good insight into what's happening in the crust. So igneous is in the mantle, sedimentary is on the surface, and then metamorphic is sort of between the two inside the crust where it's not fully melted, but not at the surface either. Oh my God. My cat just took the smelliest poop and I just got the whiff of that. Thank you, Henry, for that. This will be lovely. So we're going to start with talking about igneous rocks. And I always start with igneous rocks because this is the start, if there were a start and end, and there's not. But this is the beginning of the formation of rocks because they come straight from magma. Okay, I got ahead of myself. We classify igneous rocks through texture, which we're going to learn is glassy, crystalline coarse-grained, and crystalline fine-grained. We'll talk about these here in a second. And composition. And there are four compositional classifications for igneous rocks. There's felsic, intermediate, mafic, and ultramafic. And when I say composition, these four definitions really describe the chemical composition of these rocks, which goes down to, or brings it back down to, the mineral composition. But remember, minerals have a set chemical composition. So we might get a little chemistry in here, but I won't get too crazy, I promise. Hi, you just took a smelly poop and I need you to not stick your butt here. Thank you. Okay. So igneous rocks form when molten rock, called magma or lava, cools and solidifies. This is an image from Hawaii. This is Pahoehoe Flow. It's ropey, but this is lava that has come straight from Earth's interior. Sometimes this molten rock, which we call lava, at the surface is extrusive. It cools very quickly, right? As soon as it hits Earth's surface, it cools very rapidly. But sometimes not all magma reaches the surface before it cools. Sometimes that magma cools inside of Earth's surface, inside of Earth's crust, inside the upper part of the mantle, and we call that intrusive, right? So extrusive is cooling on the outside of the Earth. Intrusive is cooling on the inside of the Earth. Pretty straightforward. So extrusive rocks form by lava, and lava and magma compositionally are the same thing. But lava is what we call on the outside. Magma is what we call on the inside of Earth. So lava creates rocks with a fine-grained texture. And this is because that lava cools really, really, really quickly. And by really quickly, I mean it can be tens of years. When we get to geologic time, it's really fun to talk about how geologists are like, 10 years is a really short amount of time. And it can take a decade for this lava to cool and still create fine-grained extrusive rocks. This is an example of a fine-grained extrusive rock. This is rhyolite. So when I say fine-grained texture, you see that there's tiny little grains in here, but you can't really visually pick out individual minerals with this specimen just by looking at it, right? Versus intrusive rock. Now imagine you're under a blanket or in a sleeping bag somewhere, and you're tucked away and you're nice and warm. When you have something that covers you like that, it insulates you, right? So intrusive rocks, they form when magma, which is inside the Earth, create a coarse grained texture because this magma, I said lava here, sorry, that was a wrong. This magma cools very slowly because it's so insulated by what's happening outside in the Earth. And so this magma is cooling slowly, and as it cools slowly, different minerals will sort of start to segregate out of this magma. So it looks more like this. This is granite. Granite, we saw in one of the last slides, has these chunks of different minerals in it that you can see visibly with your eyeball. So this is coarse-grained crystalline, and this is fine-grained crystalline. Now it's cool, and the reason I chose these two rocks in particular, this is rhyolite, this is granite. Chemically and mineralogically, they're the exact same rock. They're going to have the exact same minerals in them, the same chemical, the exact same chemical composition. The only difference between these two rocks are the fact that this one cooled inside the Earth and created this coarse grained texture, and this one cooled outside of the Earth and formed this fine grained texture. But chemically, they are the exact same rock. So cool. Um, Within igneous rocks, we usually have seven that we look at as a whole. And something I tell my Geology 101, and actually all my geology classes, is that another really frustrating component about geology, but really cool component about geology, is that geology is on a spectrum. And again, if I were to hand this rock to five different scientists, they might come up with five different names. Granite, granodiorite, granoorthoclase. There's a number of different rocks that different scientists might interpret this rock to be. But based on its chemical composition, visually, for Geology 100 or Geo 101 class, this is a granite. These rocks are our coarse-grained rocks. These are our fine-grained rocks. And these columns, up and down, represent the composition, the chemical composition of these rocks. As we go left, we call these felsic rocks. And these rocks are lighter in color. They have more, in fact, I think I have, yeah, I do have the minerals coming up. So they have more quartz and plagioclase in this. Chemically, they have more calcium and silica and oxygen. So they're less dense. Now, as we move to the right, we get darker in color and more dense. And the sort of weird anomaly here is peridotite. Peridotite is it's our ultramafic rock. And this rock is very green. In fact, it's identifiable. It is the identifiable characteristic of peridotite, this green color. But you'll note from granite to diorite to gabbro, we get darker and darker and darker. And same with rhyolite, andesite, and basalt. So these columns, again, I showed you rhyolite and granite on the last slide. One is coarse-grained, one is fine-grained, which tells us they cooled differently, but chemically they're the same rock. Diorite, andesite, same rock, chemically. Gabbro and basalt, same chemical composition. And peridotite actually, it does have a fine-grained counterpart, but it is so incredibly rare, we rarely see it. In fact, I do have a sample of it. It's a very, very, very small sample of it. But it's a fine-grained ultramafic rock. And the reason it's so rare is because ultramafic rocks only form in the mantle, in Earth's mantle layer, which means that it cools in the mantle as well. So we rarely see a fine-grained ultramafic rock. This is Bowen's reaction series, which is a little bit more convoluted but more in-depth version of what I just showed you here, where we have our felsic, intermediate, mafic, and ultramafic list here. But then down below, this little snippy here, this little box, depicts the minerals that make up each one of these rocks. So quartz and feldspar make up felsic, but you'll note that as we start moving right, we see darker and darker minerals included in that. Obviously not going to spend too much time on this because I think this is a little bit more clear. When I say, let me move my face. I don't know where, down here. Okay. When I say that the minerals that we are looking at here are the minerals over here. So plage, feldspar, and quartz make up, and potassium feldspar. This is, sorry, orthoclase is over here, but potassium and orthoclase are the same. That is our felsic composition. As we get further to the right, we see more pyroxene and amphibole and biotite, which you'll know are much darker. And then finally, our ultramafic rocks host predominantly this beautiful, beautiful mineral called olivine, which is this gorgeous green crystalline structure up here. And that is where peridotite gets most of its green color, is from this olivine mineral. If you're familiar with like gems, this is also known as peridot. But olivine is sort of the geologic scientific word that we use for that. And within peridotite, we see pyroxene as well. So peridotite is not entirely olivine, it is also pyroxene and a little bit of plagioclase feldspar as well. We will also see other textures of rock, including a glassy texture. If you are not familiar with this rock, this is obsidian. She's another volcanic igneous rock. And she is a rock that cools so fast, like hits water and immediately cools within minutes, that she actually doesn't have time to form a crystal lattice structure. So a lot of scientists argue that technically she's a mineral because she has a set chemical composition. She's SiO2. But because she doesn't have a crystal lattice structure, she falls under the category of a rock. And she's very glassy, as you'll note. Um, and so she breaks in this very glassy-like way. We call it conchoidal fracture. She shatters like glass. This is what indigenous cultures in the past have used to make arrowheads. And fun fact about obsidian, if you make scalpels or medical grade equipment using obsidian, it actually makes it a much cleaner cut than a metal scalpel because you can make this glass very, very thin, but very, very sharp. So we talked about, let me go back briefly because I do want to repeat really quickly that our felsic rocks are light in color because of our lighter colored minerals, but remember they're also less dense because of that. And then as we move to the right, we get more and more dense as we get darker because of these darker colored minerals. So this comes back to plate tectonics. This is what we were talking about in the first video, where I was discussing how a more dense oceanic crust will subduct below a less dense continental crust. And that's because our more dense oceanic crust is made up of mafic basalt, this bad boy, and a little bit of gabbro. So oceanic crust makes up basalt and gabbro. It's very dark. Our volcanic arc, like the Cascades, the North Cascades, are made up of intermediate and felsic rocks. So we also throw felsic over here as well. Our continental crust is entirely made up of intermediate and felsic rocks, which are felsic and intermediate, these first two columns, granite, diorite, rhyolite, and then most importantly, andesite. Mount Baker and Glacier Peak, our two local friendly neighborhood volcanoes, are andesitic composite volcanoes. Um, they're entirely, not entirely, there are some other lava flows that we've done some research on that aren't entirely andesite, but Mount Baker is predominantly andesite. And then finally, let me move my face because it's covering something important. Ultramafic rocks are down here in the mantle. This is the only place they form. This is where we see peridotite. Again, peridotite is this beautiful green mineral we see here. I guess before I get too crazy, I just want to reiterate too, because this will be in your assignment, the three textures that make up igneous rocks, which are glassy, crystalline coarse-grained, and crystalline fine-grained. Okay? And the crystalline is important for reasons that you will see. So as we go through this rock cycle, we're going to go through and figure out how these different proponents make up the different rock types. So here's igneous rock down here, which forms from magma through melting. So you can melt igneous rock to form magma, or you can cool magma to form igneous rock. So that is this interaction here. No, you can cool metamorphic rock to form magma. And I'm just going to say now there's no arrow here depicting this. You can cool or you can melt sedimentary rock into magma. And basically anything that can melt into magma will turn into igneous rock, thus restarting the cycle. Let's talk about my favorite sedimentary rocks. I love sedimentary rocks so much. Oopsie. So we also, oh my God, Emily. This should say sedimentary, and I do apologize. I'll go in and fix this before I post the PowerPoint. I apologize. I do have the textures correct, though. So the textures of sedimentary rock, we also look at as being coarse-grained, but instead of crystalline, these are granular coarse-grained or granular fine-grained. And we still look at composition with sedimentary rocks, but instead of the four chemical compositions that we consider for igneous rocks, we look at these two words known as clastic and chemical. And we'll talk about all of these. Again, I apologize. This should definitely say sedimentary. So sedimentary rocks, as you can imagine, the way that they're written, come from sediments. So many sedimentary rocks are formed from fragments of pre-existing rocks, also known as detrital sediments. So these rocks might form from clay, which is a type of sediment, from silt, from sand, or from gravel. These are called clastic sedimentary rocks. Other sedimentary rocks are formed from organic material like dead things or chemical sediments, and these are known as ions. Oops. No, I didn't have anything to say about that. These are called chemical sedimentary rocks. So the difference between clastic is from existing rocks that have weathered and eroded down, and chemical sedimentary rocks that come from organic material or biochemical creations. And we'll talk about both of these. So there are 5 processes that make up, sedimentary rocks. Weathering, which is the physical and chemical breakdown of a pre-existing rock. Erosion, which is the removal of those weathering products. Transport, how this material gets moved from the original rock to a new location. Deposition, where that material stops and deposits. And then lithification, basically the cementation of these rocks. So weathering is the breakdown into smaller pieces and new compounds, and there can be physical processes or chemical processes. And erosion is the removal and transport of this weathered material by water, ice, and wind. And I have to be honest, they sort of overlap by definition just a little bit. So weathering and erosion don't necessarily mean the same thing, but it's just the breakdown and removal of original rock material. And there's different types of weathering. So, and we've seen all of it. Mechanical weathering is something like this, and it is the result of these rocks that are physically breaking down into smaller and smaller pieces. A lot of agents of mechanical weathering can be pressure, can be temperature, freezing and thawing cycle of water, plant or animal activity like root wedging, or salt evaporation. And I don't dive that hard into it. All you have to know is that it is the breakdown of material, meaning that the material that it breaks down into doesn't change chemically. So bits and pieces are being weathered off of this material, looks like sandstone, and that sandstone is going to remain smaller pieces of sandstone as it gets further and further away. So it's not changing into a new material chemically, it is just breaking off and moving away. I know, it's nuts, right? Henry's shocked. Chemical weathering, on the other hand, is particularly dominant in warm and humid environments. And it occurs when water, oxygen, and other reactants start to actually chemically degrade the mineral components of bedrock and turn them into water-soluble ions, which then can be transported by water. So, best way I can describe this is imagine that you have a mountain of sugar, Candy Mountain. And Candy Mountain has rain come down on it over and over and over and over again. Candy Mountain is going to start to dissolve, right? It's just sugar. Those sugar particles are what we call ions. They're just individual molecules. And the sugar will dissolve in the water. And as the water moves down the mountain, it carries this dissolved sugar in it. But it's not like chunks of sugar, right? It's dissolved in the water. You might not even be able to see the sugar in this water as it moves down the mountain and into a river system. If we heat that water up, that Candy Mountain is going to make that melting or that dissolving happen much faster. So this is why chemical weathering is really prominent in warm, humid environments. The warmer temperatures help speed up this process. Oh, okay. That's the only thing I had to say about that, I guess. Um, yeah. Okay. This is so in full honesty mode. This is one of my favorite topics to talk about is this process of precipitation and weathering. And I don't dive into it here, and I probably shouldn't. We don't have the time. But it's a really, really amazing concept of chemical weathering and basically breaking down these rocks over millions and millions of years into different mineral compositions and into different uh, depositional environments, so to speak. So I don't talk about it any further, which is a bummer because it's such a cool topic, but we just don't have time. So erosion is a mechanical process driven by water, which is the main agent of erosion. It is also driven by gravity, wind, and ice, and it is the removal of sediment from the place of weathering. So you can see some erosion scars, I guess, for lack of a better term, here along this sediment pile here, where clearly water has come and sort of eroded off the bottom of this sand spit. Transport is then the movement of that sediment from its provenance, which is just a fancy word of saying where the rock first was. Oh, here, it's the origin of that sediment, the rock that it came from. So transport is what moves that material. And in geology, mostly, this material is moved from river systems and stream systems, which we'll talk about in the next module. So erosion and weathering generally happens in higher topography. Not always, but it is predominant in higher topography and mountainous regions. So that erosion and weathering occurs in higher elevation, and then it gets transported down through river systems. This is not all scenarios, everything's very nuanced, but this is one of the more common methods of erosion, weathering, and transport. And then eventually, after it has been transported down this beautiful river system, it deposits, which just means that the energy level in which this material was being transported. So in a river system, this river is moving fast, right? Or it can move pretty fast. And because it's moving fast, it can carry larger materials with it. But as soon as it hits a less steep slope, um, that energy level slows down. The water, like for instance, water hitting the ocean, that water all of a sudden slows down. And because it slows down, many of those large particles will fall out of the water, of that energy and deposit. This is how deltas are formed. So these are what we call depositional environments. Basically, these are environments that form from sedimentary processes, from erosion and weathering, and transport. Where do these sediments stop? And a lot of times we see depositional environments on land. This is our terrestrial depositional environment, or marine. And this is our oceanic or marine depositional environment. And these are just different names of um, how different sediments are deposited. A lake, you're going to find really fine-grained materials in a lake because there's not a lot of energy contributed to that. Glaciers, sort of a mix. Alluvial fan, this is like a big landslide, basically. So you're going to see big chunks of rocks in an alluvial fan. A beach has a lot of sand in it because that is the capacity at which that energy can carry it. And so on and so forth. I'm not going to have you memorize every single one of these. Okay. Let me go back to this slide. So if this is where the rocks start, up in the mountainous regions, right? This is our provenance. This is the beginning of this sedimentation. As we get further and further from the source of that original rock, what tends to happen are the particles that are left behind and deposit further from the source tend to be similar in size. So if you've ever been to the beach, right? A nice beach. I shouldn't say that. I love my rocky beaches in the Sailor Sea. If you've ever been to like an Oregon coast or even the Washington coast has some beautiful sand beaches. Much of that sand is all very similar in size, right? And that is because it's well sorted. As it moves further and further away from its original parent location, it starts to lose the bits that are not the same size as it. Versus closer to the source, like in a landslide, an alluvial fan, everything just sort of dumps right? It just falls. And when it falls like that, it's every different size of particle. We call that poorly sorted. So the closer we are to the source, the more poorly sorted the material is, versus the further away, we're going to get more well sorted material. This is going to be important when we look at rocks. Um, well, I'll talk on this too. As you move further away from the source, imagine too the journey that these rocks have had to take through the stream system and out into the ocean. You can imagine that from the source, where it just dumps material, that material is going to be very jagged, very sharp, very angular. But as it travels down this stream, it's going to start to lose that sharpness because it's going to get eroded over time. There's a really cool, I know I should probably find this guy's name on Instagram or TikTok. I don't know if he's on TikTok or Instagram or both. There's this guy who has made a TikTok channel about literally just kicking rocks down the street for like hours, and he videotapes it. And what's great is he shows the before, where you see all these jagged marks and jagged bits on this rock, and he kicks it down the street for hours. And then at the end of the day, he picks up the rock and he's like, "Look how rounded it is." That's the same premise. I love it. Someday I want that to be a project for my Geology 101 class. I think that'd be a hoot. Um, to see who could get the most rounded rock. Oh, actually, this is a great idea. Thank you for the brainstorm, you guys. This was wonderful. Um, but it's the same premise. Over time, that material becomes more and more spherical and rounded as it gets more and more eroded, the further away it goes. So basically, when we look at sedimentary rocks, which we're about to here in a second, we find rocks that have roundedness to it and well-sortedness to it to determine how far away was this material originally. I'll touch a little bit on this too when we start to look at the different rocks. The other proponent that goes into sedimentary rock that I think is really important, and I put the slide in here for this, is that sedimentary rocks, the way that deposition occurs, has to occur by the law of physics, by the laws of gravity, is that as they deposit over time, they deposit in a horizontal formation. So they form in these lines. Remember when we were looking at the Grand Canyon earlier in the scientific method module? I showed a picture of the Grand Canyon. I feel like it's on here actually. Ah, look at me. I'm so smart. Here's the Grand Canyon. These layers here, they're also the entirety of Grand Canyon. Okay, that's a lie. 90% of the Grand Canyon is sedimentary rock. And it formed from a series of oceans that sat over this region millions and millions of years ago. So these layers were deposited as part of this environment that used to be an ocean. But the way that they had to form was in this horizontal layering. That's the laws of physics, right? They're not going to start to form in weird little jagged angles. They have to form in these layers. So what's cool about the Grand Canyon, besides everything, is that we still see the way that this material was layered because there hasn't been a whole lot of change to this area since these last layers were deposited. So that's all I'm getting at with the law of original horizontality, is that strata has to deposit on top of each other like this. And only then, only after that, can this strata be deformed or bent. And I'm not going to tell you how that happens. I want you to think about it. Why would we see bent stratigraphy like this? What large scale, huge, major geologic process that we may or may not have talked about in the last video could change strata from this to this or to this? If we have strata like this, how would it change something like that? Lithification is the final step of sedimentation. And um, it is basically the compression and then the cementation of material over time. And by cementation, I literally mean it is glued together through other sedimentary processes. So remember when I was mentioning in chemical weathering and Candy Mountain, Candy Mountain is getting a bunch of rain, and that rain is dissolving the salt into the water. Sometimes that rain that has that dissolved sugar will seep into the ground and become groundwater, seep into the pores of the ground, and eventually that water kind of goes away. But the sugar that was dissolved in that water stays behind, right? The sugar is not going to evaporate away, but that sugar works as a glue for rocks. And sugar in this case is actually silicate materials like quartz, like plagioclase, calcite sometimes, these different minerals that will dissolve like sugar, but they're on mountains, and then eventually make their way into pore space in the ground and will cement rocks into sedimentary rocks. So, okay, sorry, this is a little blurry, but I really liked this table because this shows the four predominant forms that are common, anyways, of sedimentary rocks. And we start with fine-grained sediment, and we go to coarse-grained sediment. And in our fine-grained sediment, what you'll know, in our fine-grained rock, this is shale, is that it's relatively homogeneous. So this is a well-sorted and rounded material. But this is so fine-grained, it's actually really hard to see with your naked eyeball. So this is a granular, fine-grained rock, texture-wise. As we get further down, we get larger grain sizes based on depositional environment. So our shale we would find in the ocean, in deep, deep ocean. Sandstone is more medium grained, but again, it's relatively homogeneous and well sorted, but it's sand grains. And if you're familiar with sand, it's basically that size. It's this crumbly sand structure, made up of multiple minerals. Uh, and this is something you'll find at like a beach, right? You'll find sand at a beach. So we're a little bit closer inland. And then as we move even more inland, we get to these very coarse-grained rocks, such as breccia, which has these chunks of rock in them, or conglomerate. And basically, conglomerate looks like cement. A lot of people are like, oh, you have cement in your class. I'm like, no, that is naturally formed. But conversely, I do have a rock in my class that has some plastic embedded in it that I like to share that this is cement, but it looks just like conglomerate. It's formed in a very similar fashion. Conglomerate and breccia generally tend to form uh, right next to the provenance or right next to the area that it was, that the parent rock was. And they have coarse grained, or it's a granular coarse grained rock. Our chemical rocks are formed from biogenic, chemical, or organic processes. I'm not going to necessarily go through all of these. Limestone is by far the most important one, I think. Basically, limestone is a biochemical rock that forms from inorganic compounds. Um, and I love limestone. It is literally the crushed up remnants of seashells that have lithified together to form a rock. That's limestone. But the shells have been so crushed, you can't really see that they're shells anymore, unless you get fossiliferous limestone. So there's a huge limestone quarry in concrete, which is why it's called concrete, because we used to build concrete in Concrete, Washington. And concrete is made up of limestone. So concrete has a massive limestone quarry, and I tried to get in there. You're actually not allowed to, and you'll get arrested. Fun fact. But I did try. But the limestone quarry in concrete has fossiliferous limestone, so you see these shell fossils within that rock, which is really cool. Chert is also really common. This is a precipitate that forms underwater. I'm not going to dive that hard into it because it's not part of your assignment. I think if you take anything out of this page without getting too overwhelmed, look at limestone. Limestone's going to be really important. So in our sedimentary rock realm, we just went through igneous rock, which is melting and cooling and melting. And in sedimentary rock, the processes that are going to form sedimentary rock are going to be weathering and erosion that forms sediment first. weathering and erosion. And then oops, more weathering and erosion. Sorry, I wasn't looking at how many arrows there were. And then finally, yeah, because that's it. Lithification or cementation. They mean the same thing. To form sedimentary rock. So these are the processes that now have taken us from igneous rock into sediment into sedimentary rock. So our last rock type, metamorphic rock, is fine. It's cool, I guess. I don't hate it. It's not the most interesting rock, I don't think, but a lot of people love metamorphic rocks, and that's fair. Um, they do form from really cool processes. Again, I forgot to switch this. I do apologize. It will be metamorphic on the PowerPoint. So when we classify metamorphic rocks, we're changing things a little bit. We do still classify with texture, but you're going to learn a new word today that is foliated. And foliation is specific only to metamorphic rocks. So you can have a foliated metamorphic rock or you can have a non-foliated metamorphic rock. Those are how we classify them for texture. And from composition, we look at the parent rock or the protolith. So what does all this mean? Um, ugh, this is one of my favorite metamorphic rocks of all time. I know I say that metamorphic rocks are the least cool, and they are the least cool, but they're still really cool. So if you've driven up the North Cascades Highway and you've made it all the way to Diablo Lake, which if you haven't, highly recommend. If you make it to the Lake Diablo overlook, which is up pretty high, and you turn around and you look at this giant wall of rock, this is one of the coolest metamorphic rocks in the North Cascades. This is called a migmatite. And we're going to learn about the processes that make up a metamorphic rock. And I'm going to come back to why this is the coolest rock. This is why this is the coolest metamorphic rock. So foliation occurs in metamorphic rocks. Okay, I don't know why I put that one there. We're going to come back to that slide too. Because a metamorphic rock just means that a rock is changing. Metamorphism is just the transition of one rock into another through high temperatures and or pressures, unlike those in which it formed. So sometimes it can change the mineralogy and sometimes the chemical composition in a solid state, but it never gets to fully melted. So when you fully melt a rock, it goes back to igneous, right? It goes back to magma, back to lava, which makes it an igneous rock. But you can start to heat a rock to the point where it becomes very malleable. And a lot of the chemistry within that rock might start to like wiggle around a little bit. In the last video, we talked about how the mantle was very malleable, but it was not liquid, nor was it solid. This is the same premise in that these rocks can get so hot that they can sort of move and jiggle a little bit, but they'd never become fully liquid, and they can sort of move as a solid. Which means that every metamorphic rock comes from another rock. And we call this the parent rock or the protolith. So parent rocks can be igneous, they can be sedimentary, or they can be other metamorphic rocks. Basically, it is a rock that is put into a situation where either pressure starts to smoosh it, or it becomes deep enough in Earth's crust, not the mantle, but Earth's crust, that enough heat starts to really alter that rock material into a different rock. And the degree in which this change happens is called the grade. So metamorphic grade is the degree to which the parent rock changes during metamorphism, meaning that let's have a granite. Okay, I have a granite. And slowly this granite starts to get smooshed. This is a low grade rock, low grade change. The more and more we see the smooshing, the higher grade this rock is going to be, or the higher smooshed this rock is going to be, until we get to a rock called gneiss. I should say nice. I know that's how you say it, but I have to say gneiss. So until you get to a new rock, which is metamorphic. Or conversely, you get a granite and it gets deeper and deeper buried into Earth's crust. So there's more heat that is applied to this rock and it begins to get a little bit more malleable. The more malleable it gets, the higher grade it gets as well. And the higher grade that these rocks become will alter the foliation of these rocks. So foliation describes the planar arrangement of mineral grains or structural features within a rock. So, okay, this is where I want to go back to this page. We have an example of a rock that is becoming more and more higher grade rock, meaning we have lower temperatures and lower pressures starting here. The more pressure and the more temperature that we apply, the higher grade this material becomes, which also means the more foliated the material becomes. Now, foliation can either be, and this is where I know metamorphic rocks, I think the reason I think they're a little less cool is because there's a lot of weird shit that happens with metamorphic rock. In that, with foliation, it can mean one of two things. Either we see physical foliation, which looks like very flaky layers. So when we see slate, slate has this very physical and flaky type of layering in it. Then we're going to get to phyllite, which has a little bit more flakiness to it. It also starts to get shiny because all those minerals, as this rock is getting more and more smooshed, all these minerals are starting to align. Okay. And as they align, this rock becomes a little bit shinier because all the faces of this mineral are going to start to face in the same direction, if that makes sense. Schist, we still see physical foliation here. We see layers here, but we get some shine with schist. Look at this sparkle. She has a lot of uh, biotite and muscovite in her, which is a mica. And mica is very flat and very planar and has a beautiful shine to it. But then finally, we can also see colored foliation. I call it colored foliation. A lot of geologists would be like, it's just foliation through and through. But I like to differentiate the sort of physical foliation of this like flakiness with this colored foliation, which is basically that this gneiss, which I should say nice, you're not supposed to pronounce the G, but I can't do it. This gneiss has been so pressurized and so smooshed and probably likely pretty heated deep in Earth's crust that the minerals got so hot, they actually started to migrate out of the rock system. So this would be like the parent rock to this would be a granite or even a shale. So the minerals in here began to separate out and segregate and band based on the pressure being applied to this metamorphic rock. So we call this foliation because these are very parallel delineations of color here, but they're not necessarily a physical flakiness, but they're still parallel and they're separate. So this is a gneiss. Now, in these rocks, the slate, phyllite, schist, and gneiss, the common factor between all of these is that the parent rock of this series here had multiple minerals in it, which allowed those minerals to start to flatten out. So you could see the sheen as we get higher and higher grade. And eventually in our gneiss, those minerals separate out. So the black is one mineral, roxine probably, and the white is another mineral, quartz. So these are multiple minerals within a rock that make it this, that give it this really nice foliation. However, we also see metamorphic rocks, usually applied with heat, usually the only proponent of forming this. So there's not a lot of pressure applied to these two rocks here. It's mostly like heat. This happens predominantly next to like magma chambers, where it's not in the magma chamber, but the heat radiating out from a magma chamber is hot enough to melt. I'm sorry, I shouldn't say melt, that's the wrong word, to affect some of the rocks sitting near it, which will alter those rocks, but not physically smoosh them or foliate them. And we have rocks like quartzite and marble, which we call non-foliated rocks. And these non-foliated, you don't see, I fully admit that these two rocks are very difficult to identify in the field because you don't have that foliation. At least with these foliated rocks, you can be like, oh, it's a foliated rock, meaning it's metamorphic. A lot of times I'll pick up a quartzite or a marble and be like, maybe it's quartz, maybe it's feldspar, I don't know. Because you can't see that foliation. You have to do other tests to ascertain if these are non-foliated. And I'm not about to quiz you on non-foliated metamorphic rocks because they're really fucking confusing. Um, but the reason I still have it in this slideshow is to show you that we have foliated metamorphic rocks, but non-foliated metamorphic rocks. And the other difference between the fact that these likely don't have a whole lot of pressure applied to them, even though they might have a lot of heat, meaning they can still be high grade. If we still have a lot of heat altering these rocks, that can be high grade. The other proponent in this is that both of these rocks are comprised of one type of mineral. This tends to be quartz. Quartz sandstone is the parent for quartzite, and then limestone is the parent for marble, which remember is the smooshed up proponents of clamshells, or seashells, I should say, not just clams. Um, this is just another depiction of foliation, and I tried to put a few different depictions in here because I understand that metamorphism is really weird and it's kind of hard to wrap your brain around if you're not looking at the physical rock. But you'll note that the texture as we go on becomes linear and planar. Sometimes you get this wavy texture, but you'll note even the waves are still parallel to each other. And then we start to see colored banding because of the segregation of these mineral ions. And then we have a non-foliated metamorphic rock, which is comprised entirely of a single type of uh, material. Limestone is just calcite, and quartz sandstone is just quartz. Again, just another depiction. I wanted to put as many depictions in here as I could, but it's saying the same story that the other two slides just said. So if this one helps you understand a little bit better, awesome. I gotta be honest, I don't know why I put this slide into this particular PowerPoint. It's just the minerals that we see in metamorphic rocks, but I don't want to sit on that. I don't think it's important. So we have gone from magma, which is the melting process, to igneous rock, which is a cooling of magma. Anytime you melt, you fully melt, turn to liquid, any rock, and it becomes magma, that magma is only going to cool into igneous rock. You can weather and erode any type of rock to become sediment. You can erode metamorphic rock, sedimentary rock, igneous rock. You can erode anything. And through that sediment and over time, that sediment will lithify and cement into sedimentary rock. And finally, for metamorphic rock, the only way to form a metamorphic rock is through pressure and or temp. You can do that with sedimentary rock. You can do that with igneous rock. You can do it with another metamorphic rock too, but it would have been weird to put another arrow up here. So this is the full rock cycle. And it doesn't have to be this way either. You can turn sediment into sedimentary rock and turn that sediment rock into magma right away. You can do igneous rock straight into metamorphic. Like it's not set in a, it has to go round and round and round. It can be like boop, 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 boop. It's very subjective. And the entire rock cycle, every single rock type, metamorphic, igneous, and sedimentary, are all on a spectrum. That is so important to note, that it is all on a spectrum where there's in-betweeners that scientists struggle with really understanding. Well, I think it's this and I think it's this. And that's okay. It's part of this science. So when we investigate rock, every rock has a story. I love that so much. It's why I love geology. We use these physical characteristics, including the textures that I just walked you through, and the chemical compositions to infer how and where the rock was formed. And this tells the story and the geologic history of the rock. Asking these questions will get you started on interpreting the geologic history of the rock. What did the rock form from? Where did the rock begin forming? Where did the rock finish forming? And what happened to the rock after it formed? So let's put it all together. We just walked through the entire rock cycle. Where do we see these rocks in local areas? Okay, I took this picture on Bellingham Bay. So this was up in Bellingham. That's one of my favorite photos. Here's Bakey, Mount Bakey, our beautiful, friendly neighborhood, Mount Baker volcano. This is from a different vantage than how we see her in Skagit, but still the same mountain. This is Coleman Peak. Is it Coleman Peak? Okay, I'm gonna get back to you on that. I'm questioning everything. There's a Coleman Glacier on here, but now I'm questioning that this is Coleman. I'll get back to you. These are the twin sisters. We live right next to the twin sisters, and this is not the only time I'm going to talk about twin sisters, because I'm going to talk about this a little bit in the anthroposphere module that I have later on down the line. But Baker and the twin sisters are two different igneous rocks. Um, they're located here. So here is Mount Burney. The twin sisters are directly northeast of us, and Mount Baker is just behind her, just behind them. The sisters, actually, we call them the twin sisters, but there's actually about 12 of these peaks throughout the series of these mountains. Um, and what I love about them, this is the coolest thing. So note, they're right next to each other, okay? Right next to each other. Hold on, hold on, hold on, hold on. I hope uh, it's all worth it here. Okay, Mount Baker is predominantly andesite. She has a little bit of rhyolite on her as well. I've collected rhyolite on her and andesite. And for some reason, she has a little bit of basalt flow as well. Very minimal. It's very small. It tells a different story. But Mount Baker is predominantly andesite and rhyolite, meaning that she's from the continental crust. That makes sense. That tracks, right? She's sitting on the continental crust. The twin sisters are entirely different compositions. They are peridotite. And if you remember, peridotite is an ultramafic rock that forms only in the mantle. So the twin sisters wildly, yes, let me go back to her. The twin sisters were formed in Earth's mantle, so 12 miles under the surface, probably closer to like 8 miles under the surface. And over the past probably 30 million years, 20 million years, they have been pushed up from Earth's mantle to the surface to where they are now, and they've eroded into these beautiful peaks. But these two mountains sit right next to each other. Mount Baker is continental in composition, and the sisters come from the mantle. That's fucking wild. I cannot express. I mean, I've already expressed in one of these modules how incredible geology is here in the Pacific Northwest. It is incredibly rare to find peridotite and olivine, the mineral olivine, at Earth's surface. And we have some here at the Twin Sisters. We also have some out here in Washington Park. It's like fucking wild how much peridotite we have in this area that has come from the mantle and been pushed up. And it's been pushed up because remember, we're on a subduction zone, and this subduction zone is basically pushing up the continental crust. It's being uplifted. So everything in this region is being smooshed and uplifted. And then eventually everything at the top is being eroded. So we're being smooshed, uplifted, and eroded down. And that allows really incredible features like the twin sisters from the mantle to be present and accessible at Earth's surface. It's so wild to me. This is like one of the coolest things about this area. And we'll come back to this because one of the biggest mines in this area is from the Twin Sisters. We mine olivine for very specific reasons. Sedimentary rocks are also everywhere in this area. This is the Chuckanut Formation. And the Chuckanuts, here we are this beautiful green deposition right here. And we're going to talk more about the Chuckanuts in the fossil lab, so biosphere. Because the Chuckanuts have these incredible fossils throughout. And I went fossil hunting in the Chuckanuts this year, and it was amazing. And I found incredible fossils that look like this. This is a palm frond, so a palm leaf, basically. If you've never been through the Chuckanuts or down Chuckanut Drive, also highly recommend. Larrabee State Park is stunning. It has a lot of these really beautiful weathering um, features. So we talked physical and chemical weathering. This is a physical weathering process called taphony that we see a lot of along the coastline. And most of the chuck nuts are sandstone, shale, and conglomerate. We also see some coal embedded through these sedimentary rocks. And that's because the Chuckanets used to be a massive riverine system. So, like a river on the scale, think river on the scale of the Columbia River, fucking massive. And it formed about 55 million years ago. Um, and it just has created this incredible sedimentary structure uh, in this area. It's one of my favorite places of all time. And the third type are metamorphic rocks. And our metamorphic rocks are predominantly, as you can imagine, in the Cascades where there's a lot of smooshing, but there's a lot of depth down there too. And metamorphic rocks need crustal depth. So they form in the crust, right? They don't go all the way down to the mantle. They form in the crust. There's a lot of pressure involved in the smooshing of the Cascades. So a lot of metamorphic rocks are up in the Cascades. So here is just an abundance of where we see several metamorphic complexes. All together, we are right next to, and again, this makes this area so just incredible and mind-boggling because there are places in the United States where you're like, well, there's a bunch of sedimentary rocks here, or there's a bunch of igneous rocks. It's not necessarily rare to say that you have all three types in one location, but it is spectacular and it is incredible. And the stories that these rocks tell are just like mind-boggling and amazing. And it's so fun to read these stories and really look into how this whole area was formed. We're right next to metamorphic, we're right next to igneous, and we're right next to sedimentary. And I want to go back because I said I would, because, oopsie, shit, you got some Google Earth there. This rock that I told you I'd come back to is a metamorphic rock, and it is the highest grade metamorphic rock that we can get to, that we have assessed. So highest temperature and highest pressure associated with the metamorphic process here before it turns to melt. This is called a migmatite. And a migmatite basically becomes so liquefied without becoming magma that it is the most high-grade metamorphic rock that we have been able to analyze and assess. And we have this incredible outcrop of it right across the street from the Diablo Lake overlook. So if you ever get the chance to go here and see it, you'll see like these like wavy, sort of crazy lines of this calcite and this quartz, basically indicating that it was so malleable at the time, at its highest metamorphic moment, that it just sort of like moved like liquid without it being liquid. And then it cooled like that. So again, didn't turn to lava, didn't turn to magma, but it was so hot and so pressurized that it became very close. And so we call this a migmatite. It is the coolest rock, the coolest metamorphic rock, pardon me. Okay, so that is what I have for rocks and rock cycle. Keep those textures and the compositions in mind when you do the homework. I will change those slides. I do apologize. I just didn't catch it in time, and I don't want to go re-record this video. So let me know if you have any questions or concerns, and I'll see you for hydrosphere.